Look at this heavy metal sphere. It has a specific weight, a defined surface, and takes up space in our standard three-dimensional reality. In this familiar environment, the laws of physics are absolute. The conservation of mass dictates that matter cannot be generated out of thin air. This diagram illustrates how physical division is a zero-sum game. Slicing a sphere into 4 equal parts means those 4 physical wedges will always add up to exactly the original volume. 1/4 times 4 is 1. In this standard Euclidean space, it is physically impossible to create something out of nothing. Yet in 1924, mathematicians Stefan Banach and Alfred Tarski published a theorem about disassembling a solid object that bypassed these physical limitations. They proved you can break that original sphere into finite pieces, reassemble them, and end up with 2 complete spheres, identical to the first. We know instinctively that one object cannot become 2 identical objects without adding new material. The mystery lies in how a mathematically sound theorem can sidestep our understanding of volume and mass without breaking the rules of logic. To understand this, we have to look past physical matter and examine the object strictly through the lens of theoretical geometry. Here, we see a representation of our object, but instead of atoms, it is built out of an infinitely dense cloud of individual mathematical points. Because this set of points is infinite, it possesses a unique property. You can remove half of the points and still be left with an infinite amount. Unlike a finite object, an infinite set can be divided without exhausting its contents. This means we can no longer rely on the physical intuition of separating an object into solid, continuous chunks. The tool mathematicians use to sort these infinite points is called the Axiom of Choice. This axiom allows us to select specific points from the sphere to create scattered patterns rather than clean, solid wedges. The sphere is sorted into 5 distinct sets. These non-measurable sets are so scattered they have no defined surface area or interior. As we attempt to measure them, the calculation fails. Lacking continuous boundaries, they do not possess an assignable volume. By using sets that lack a measurable volume, the mathematical requirement that the parts must sum to the original whole no longer applies. And now we reach the reconstruction phase. Taking these non-measurable sets and combining them requires only simple geometric shifting and rotation. Watch as 3 sets rotate and shift into place. The density of infinite sets allows these scattered points to interlock perfectly, forming a single complete sphere. The remaining 2 non-measurable sets undergo the exact same rotational shift, independently forming a second identical sphere. Rearranging an infinite supply of points ensures that both resulting spheres are fully dense. Proving the paradox is a logical certainty. There is a lasting tension between this mathematical result and the physical world we experience every day. The Banach-Tarski Paradox is a consequence of the Axiom of Choice and the properties of infinite spaces. It demonstrates that advanced mathematics is a standalone logical framework, capable of describing structures that follow rules different from those of the physical objects we can touch.